Alright, so today we're going to talk a little bit about the basics of a geometric sequence. So we're going to start with our objectives. And our objective is to recognize and extend geometric sequences, and then also be able to find a term in a geometric sequence. And then we have some vocabulary: geometric sequence and common ratio. So geometric sequences can be thought of as functions. The term number, or position in the sequence, is the input, and then the term itself is the output. And so geometric sequences function very similarly to the way arithmetic sequences function, where you put a number in your input, and you get a number out your output. So we're going to input a position, so this would be like a to the 1, a to the 2, a to the 3, or a sub 1, a sub 2, a sub 3, a sub 4. And we're going to get out an output. So a sub 1 equals 3, a sub 2 equals 6, a sub 3 equals 12, so on and so forth. Now, to find a term in a geometric sequence, you have to multiply the previous term by r. Now, it's really important we know what r stands for. R is a ratio. So, in this case, it's pretty obvious that our ratio, or what's happening, is every single time the number in the sequence is doubling. And doubling means to multiply something by 2. 3 times 2 is 6. 6 times 2 is 12. 12 times 2 is 24. But how do I find r? Like, if it's not given to us, how do we figure it out? So I told you, r stands for ratio. And when you hear the word ratio, I want you to think of division. But why division? Because weren't we just multiplying? Yes, division. Here's why. We looked at this sequence on the page before. So we had 1, a sub 1, a sub 2, a sub 3, a sub 4. A sub 1 is 3, a sub 2 is 6, a sub 3 is 12, a sub 4 is 24. And we said that each and every single time it was being multiplied by 2. Well, in order to find r, I look for this position, so my fourth position, and I'm going to divide it by my third position. 24 divided by 12 is 2. Now I'm going to look at my third position, and I'm going to divide it by my second position. 12 divided by 6 is 2. Now I'm going to look at my second position, and I'm going to divide it by my first position. 6 divided by 3 is 2. So that's how we get our ratio of 2. Now, how do we use this in the real world? Well, think of it like this. If you bounced something, does it come back the same height every time? Or does it slowly get lower in height? I hope you said slowly get lower in height, because if not, you'd be in outer space. But what we do know is that it doesn't lose the same amount of height each and every single time. So we'll look at this example. This table shows the heights of a bungee jumper bouncing. Now, not bouncing off the ground, like, a bungee jump is elastic and it bounces back up. So, the first bounce, the guy or gal comes back up 200 feet. The second bounce, they only come back 80 feet. And the third bounce, they only come back 32 feet. Now, I know this is not an arithmetic sequence because we don't have a constant difference. The difference between 280 is not the same as the difference between 80 and 32. So in order to prove if it's a geometric sequence, I need to find if it has a common ratio. And I'm going to do that by this. I'm going to take 32, my third number in my sequence, and I'm going to divide it by 80, my second number in my sequence. 32 divided by 80 is 0.4. Now, this will be a geometric sequence if my second number in my sequence divided by my first number in my sequence is also 0.4. And it is. 80 divided by 200 is 0.4. So that means every single time in my sequence, I am multiplying by 0.4. So if I wanted to find what the fourth number in the sequence was, I would take 32 and I'd multiply it by 0.4. The height of the bounces in this table does form a geometric sequence. In a geometric sequence, the ratio of successive terms, which just means one term after the other, is the same number, r, also known as the common ratio. And that is the difference between an arithmetic sequence and a geometric sequence. Arithmetic sequences, you're adding the same number over and over and over again. In geometric sequences, you're multiplying by the same number over and over and over again. So, we're going to look at example number 1, extending geometric sequences. Let's find the next three terms in this geometric sequence. So my first term is 1, my second term is 4, my third term is 16, and my fourth term is 64. First thing I need to do is find my common ratio. And remember, I do that by dividing. Ratio, R is ratio. Ratio means division. Now, in order to check and prove that this is a geometric sequence, all of the ratios have to be the same. So, I did 64 divided by 16, that's 4. 16 divided by 4, that's 4. And 4 divided by 1, that's also 4. So this is a geometric sequence. So how would I find the next three terms? I'd start multiplying by 4. So 64 times 4 is 256. That'd be the fifth term in the sequence. 256 times 4 is 1024. That is the sixth term in the sequence. 1024 times 4 is 4096. That would be the seventh term in the sequence. Okay, find the next three terms in the geometric sequence. So, let's see what we can do here. Remember, the first thing we have to do is find the value of r, which is our common ratio. We do that by dividing each term by the one before it. So, we're going to say negative 1/9 divided by 1/3 is negative 1/3. Negative 1/3 divided by negative 1 is negative 1/3. Negative 1 divided by 3 is negative 1/3. And 3 divided by negative 9 is negative 1/3. All of these numbers share the same common ratio. So we have to find the next three numbers in the sequence. So I'm going to say we're going to multiply each term by negative 1/3. So negative 1/9, negative 1/27, negative 1/9, 1/27, negative 1/81, and positive 1/243. Now, why is it going back and forth between negative and positive, and then negative and then positive? Well, I want you to ask yourself, remember your integer rules. A negative times a negative is a positive. A positive times a negative is a negative. A negative times a negative is a positive. What will be the sign of the next number in the sequence. Okay. To find the output, or a to the n, of a geometric sequence, when n is a really large number, you need an equation, or a rule. Very similar, like we needed a rule for arithmetic sequences, we need a rule for geometric sequences. And they have most of the same parts. We have a, or we have a to the 1, and we have n minus 1, and instead of d for difference, we have r for ratio. So here's what I want you to notice. We have our very first term is 3. And 3 is going to get multiplied by a common ratio of 2. And then it's going to get multiplied again by 2. And then it's going to get multiplied again by 2. So when we talked about arithmetic sequences and we said that repeated addition is multiplication, well, repeated multiplication, or times 2 times 2 times 2 times 2, that is an exponent. So our formula, or our format, is a to the 1, or our first number, times our common ratio to the n minus 1. And the n minus 1 is an exponent. Let's see what that looks like. So, a to the n, or a sub n. I keep saying a to the n and I'm wrong. A sub n. Any number is the first number times the ratio to the n minus 1. So we have our nth term, this is what we're looking for. We have our first term, this is what we have. We have our ratio, they either give that to us or we have to find it. And then the n minus 1. And remember, it's always n minus 1, because if I have my first term, I'm making one less move. So like if I have my first term and I need my 8th term, I only have to move 7 times to get to 8. 1 plus 7 is 8. Okay, we're going to do this example. For a geometric sequence, a sub 1 is 5 and the ratio is 2. Find the 6th term of the sequence. So we're going to write our formula. A sub n, or any number, equals a sub 1, our first number, times our ratio to the n minus 1. So we're going to substitute everything we have into our formula. And I'm going to say a sub 6 is the same as, or equals, 5 times 2 to the 6 minus 1. We're going to simplify our exponent. So 5 times 2 to the 5th. And that's 160. Okay? So let's think about that out loud. I start with 5. I multiply that by 2. I get 10. I multiply that by 2. I get 20. I multiply that by 2. I get 40. I multiply that by 2. I get 80. I multiply that by 2 and I get 160. That is 6 times for our 6th number in the sequence.